Okay, so this video is going to be about sigma notation, which just is a tool that you can use to represent a sum of many different numbers added together. Okay, so let's start with saying precisely what the notation means. So let's say you had some numbers. And in particular, I'm going to say, suppose we have an array of numbers. So I'll say A1, A2, and then I'll keep on going all the way up to some term, say AN. So you can see I've used index A1, or an index of 1 here for A1, index of 2 for A2, and so on. And then the very last index is N. So let's say that all those are real numbers, and we want to add them all up. Well, this notation will allow you to do that very nicely. So here's how it looks. First aspect of it, this is why it's called sigma notation, or it's also called summation notation, but it involves the Greek letter sigma, which is like a capital sigma. So what are we going to add up? That's the next thing we have to say. We're going to add up all these terms. So I want to add up all the A's for every possible choice of index. So what I'm going to do is I'm going to say AJ. So I'm indicating that I'm going to add up the A terms where J is a letter used for the index. Well, what values of J would I want to consider? Well, the first one is J equals 1. That's the very first term here. So I'd say J is equal to 1. And how far is it going to go? Well, it's going to go from 1 to 2, and so on, all the way up to N as the very last value for the index. So that's why I'll put an N up here. So that's the notation, and what it means by definition is it just means this, A1 plus A2, and so on, all the way up to the very last one, AN. Okay, so that's what the notation means, and it just allows you to efficiently express sums of numbers. Let's look at an example where we actually compute one of these sums. So let's say I define a sequence, AJ, in terms of the following formula. So the term in the sequence that has an index of j is going to be given by the formula 2j squared minus 1. And that's going to be true for every value of j which is greater than or equal to 1. So this is an example of a sequence of values defined by a formula in terms of the index. And what we're going to do in this example is we're going to compute the sum from j equals 1 to 5 of aj. So it's kind of like this notation, except instead of an unknown stopping point, n, we have a fixed stopping point, 5. So you're just going to add up aj, where j is allowed to range from 1 to up to 5. So let's see what that looks like when we actually work it out. The first step is to unpack what the summation notation actually means. So let's just start by rewriting what we're going to compute. That's our first step. This is what we're evaluating. So the first step is to deal with this summation. Let's expand the sum. That's what this is referred to as. So what you're going to do is you're going to look here and say, okay, this is what you're adding up. Every single term in your addition is going to come from this expression. But then you're going to consider values of j, starting with this value down here. So if I plug j equals 1 into this expression, I'm going to get a1. So that's the first term in my addition. What happens now if I increment j by 1? That'll take me up to j equals 2. So plug in j equals 2, and I get a2. Now I increment j again, and I'd have j equals 3. So plug that into here, and I get a3. Increment j again, you get 4. So add up a4. Increment it one more time, and you're going to get 5. So that gives you a5. And you know to stop now, because this 5 up here is what indicates that that's the last value you're going to consider for an index. So this is the expansion of this sum. Okay, great. Well, now we can go a little bit further, because each of these 5 values are defined in terms of this formula. So let's use this formula to actually work out what these are going to be. So on the next step, I'll say a1 is going to be 2 times 1 squared minus 1. So this will be 2 times 1 squared minus 1. I'll just put square brackets around that to indicate that that's all one term. It's just easier to read that way. Now a2, well, plug in 2 for j. You're going to get 2 times 2 squared minus 1. Okay, great. Now plug in 3 for j. We're going to get a3 is equal to 2 times 3 squared minus 1. a4 will be 2 times 4 squared minus 1. And then the very last one will be 2 times 5 squared minus 1. And that's really just, now we've replaced each of these symbols with what they actually mean, which is use this formula to actually find out what their number is. Okay, so let's just work out these individual pieces. It's a little easier to do this first. So 2 times 1 squared, that's just 2, right? This whole first term is 2 minus 1, so this is equal to 1. 2 times 2 squared, that's 2 times 4. So you subtract 1 and you're going to get 7. This will be 2 times 9, which is 18. So minus 1 and you get 17. 2 times 4 squared is 16, so that's 32 minus 1, which is 31. And then what's the last one? 5 squared is 25, so 2 times 25 is 50. So this is 49. And actually, if you can add those up however you like, you're going to end up getting 105 as the answer. So I actually have room over here. I'm just going to squeeze it in right here. So that's what the sum evaluates to. So that's 105. That's what this really means. That's what it works out to be. Well, I should say this. It really means this. It just happens that it evaluated to 105. That's probably a better way to say it. Okay, so that's one example. Another example could be the function defined in the following way. And then use this function to come up with summation notation that uses it. So let's define function f by f of x equals 4x minus 10, right? That's a function from the real numbers to the real numbers. You can plug in a real number and you'll get as output some real number. Now let's compute the following sum. This is going to be the sum from k equals 2 to 3 of f of k. So is this valid? Does this match up with this notation? Not exactly, right? Because the bottom, well, the index for starters, I've used the letter k for the index. Well, that's no problem. As long as I say what the index is, and then this expression over here uses that index, that's fine. I can still just use this as my stopping value for the index. So I've used a different letter for the index, that's no problem. And instead of a 1, which you see up here, you see a 2 down here. Well, that's no problem either. This just tells you what the initial value for the index is. So we can also make an adjustment for that as well. So this will be no problem. What will we get? Well, start by just writing out what we're computing. The sum from k equals 2 to 3 of f of k. Well, start with your initial value of your index, which is k equals 2. Plug it into this expression. What do you get? Well, you'll get f of 2. Right? If I plug in k equals 2 to f of k, I'm going to get f of 2. So that's your first term. Now you go back to your index and you increment it by 1. And that's going to take you up to k equals 3. The next term is going to be f of 3. Now I don't go f of 4, f of 5, f of 6. I don't just keep on going because 3 is the last value of the index that I should consider, right? So that's how I know to stop here. So from here now I just need to evaluate what f of 2 and f of 3 are, and for that I'll use the definition of the function. So what will we get? Well, f of 2 is going to be 4 times 2 minus 10. So that's f of 2. And then f of 3 is going to be 4 times 3 minus 10. And that works out fairly nicely because this is going to be 8 minus 10, which is negative 2. And this one's going to be 12 minus 10, which is positive 2. So if you add those up, you actually get 0. So this sum evaluates to 0.